All right, it's my pleasure to introduce Carly Nilson and Michelle Tang, who will talk to us about how the Swamp Water Board shares data with the public. Go ahead and take it away.
Thank you. Oh, she is. Okay. I'll keep it just in case. All right, so good morning, everyone. My name is Michelle Tang. I am an environmental scientist at the State Water Resources Control Board. And as mentioned, I'm presenting with my colleague, Carly Nilson, who is joining remotely today. So for our presentation, we will be highlighting two data visualization tools that we've developed in SWAMP and talking a little bit about how we use these tools to better communicate and share our data with the public. So as you'll hopefully see, these two tools are quite different, both in kind of how they're designed and also the specific use cases that they serve. But the overarching goal is to make SWAMP data more approachable and accessible for everyone. So I'll be starting us off with some slides about the SWAMP data dashboard, and then Carly will follow with an overview on the FHAB incident reports map. Okay. So I'm going to race through the slide, but very quickly, SWAMP is an ambient monitoring program. We were catered back in the year 2000. We conduct monitoring both at the statewide level and then also the regional level. So our bioassessment program is one of our statewide monitoring programs. And we collect measurements on a wide range of chemical, physical, and biological properties at sites throughout the state. So in a nutshell, SWAMP generates a lot of data, and one of the goals of our program is to make all that data available for everyone inside and outside the water boards to use. Okay, next slide, I guess. I'm not sure, so the slides there changed, but not this one. I'll go off that screen. Okay, so one way that we hope to make SWAMP data more accessible is through the SWAMP data dashboard. And this is a web-based interactive tool that you can use to explore and download SWAMP data. So you can interact with data both at the statewide level, which is what we're looking at here, and then also the site level, which I'll be going through in the next couple of slides. So just to highlight some of the main functionality of it, there are a series of filters kind of on that left hand panel there, and you can use those to narrow down and find what data you're looking for. There is a search bar at the top right, which you can use to locate a specific monitoring site or water body that you might be interested in. And then also you can switch back and forth between the map view, which is what's being shown here, and then also the table view, which displays a lot of that same information, but in a tabular format. All right, so to view data at the site level, you would want to select an analyte from that previous screen, and then also select a site from either the map or that table. And that will generate the view that you see here, and then also that time series plot showing all of the available data that we have for that selected site and analyte. So for this specific example, we're looking at Arroyo Grande Creek at 22nd Street. And then I've also picked the CSCI, the California Stream Condition Index. And for this specific site, you can see we have CSCI scores from about 2001 to about 2007. And then also in the background, you'll see that we have the CSCI score categories also depicted there in different colors. So you can see where those scores fall kind of over time and what that means in the greater context. Directly above that, we have a download data button that you can use to generate a CSV file with all the data points that you see in that chart. Also from the site view, you can graph or compare data across multiple sites. So what you're looking at now is that same site and analyte that I selected before, but the difference is that I've also added 2 upstream sites from the map there. The graph has also been updated to include all the data from all 3 sites. So you're looking at that on the same plot. And hopefully it's not too difficult to see, but each site is depicted in different colors. There's an interactive site list or legend in the bottom there that you can use to add or remove sites. And then also the download data button at the top has also been updated to include the data for all 3 sites or however many sites that you select. Another way that you can explore data using this dashboard is through the site pages here. So basically, every unique swamp monitoring site has its own dedicated view or page that you can use to get an overview of all of the available data at that site. So this could be very useful if you're looking to do a deep dive into one site and you just want to see what's going on there. So it'll give you a list of all the analytes there, the volume of data, how recent that data is, and then it will also generate some statistical calculations like average, minimum, and maximum for each one of those analytes. From the site page, you can also graph multiple analytes for a site at one time. So you can select up to 5 analytes and it will generate however many charts as needed, and it'll kind of stack them on top of each other like that. And the date range for the x-axis there will be consistent across all the multiple charts. So you can use that to compare data over time or spot any gaps or patterns in the data. So for this specific example, I've selected turbidity data, which is shown here on top. It's hard to see, but that's the same CSCI data set that I selected before. So they're stacked on top of each other and you can just scroll through them. All right, so that was a very quick overview of Swamp Data Dashboard and some of the main functionality it offers. In summary, it's designed to be an integrated platform that combines multiple data types and makes it easier to download that data from a single spot. Very important to note, however, that this is currently a work in progress. So there's still a lot of work that needs to be done. And also a big thing is that it doesn't have all of SWAMP's data yet. So we're kind of adding data in phases. And not all the functionality that we have planned for it is in there. But right now, the currently available data sets include our conventional water quality parameters, chemistry data, toxicity data, and then also our CSCI and IPI scores. The next version of the dashboard, which is actually coming out pretty soon, will include all of our tissue data, and then we'll be following that up with our bioassessment and FHAB program data. So finally, I just want to mention that this data is sourced from CDEN, which is the California Environmental Data Exchange Network, and it's refreshed on a weekly basis. So we do quite a bit of processing to all of our data. So this tool doesn't have, a fast refresh rate, maybe compared to some other tools, but it does allow us to deliver a product that is focused on displaying long-term data and trends. And, we'll be integrating the trends part a little bit later. But yeah, so that's all I have for my overview. I'll go ahead and pass it off to Carly now, who will give us another overview about the FHAB program and incident reports map. Thank you.
Hi there, everyone. It's taking a minute for the slides to catch up, so my apologies, but my name is Carly Nilson, and I co-manage the Freshwater and Estuarine Harmful Algal Bloom program at the State Water Board, and I'm going to give you a quick overview on our HAB web map today. Okay, so I just want to give a little background first. As to our Freshwater and Estuarine Harmful Algal Bloom program, you'll hear me call it FHAB for short, because that's a mouthful. The program became formalized with the passing of Assembly Bill 834 in 2019. And although we are mandated to do a lot of stuff, the one I want to highlight today is one of our primary mandate goals is to communicate harmful algal bloom notifications and risks to the public. So that's going to be the focus today. So how do we do that? With the help of our data scientists in OEMA, including Michelle, who just spoke, we're a small but mighty team, we developed a map to share recreational advisories to the public. So we receive reports of HABs through an online report form through our portal. And then this is often from the public and local agencies sharing. And we also receive reports through the California Poison Control Services. And of course, data and information from our internal water board sampling efforts, and also partner monitoring data that's shared with us. And all of this information is then funneled into our FHAB program web-based database, where staff internally then QA the data before publishing it for the public on our HAB web map. And we try to be as efficient as possible in making sure that information is translated to our map within 2 business days, so the public is kept aptly informed. And this is just to quickly highlight the magnitude of the data we receive and publish to our map each year. Last year in 2022, we took in 680 new reports, and that isn't even counting the reports that are updated, which I'll talk to in a moment. But this effort obviously couldn't be accomplished without a lot of help on the back end. So the names in green are the water board staff that are funded through the Assembly bill. As you can see, there's not a lot of green names there, only 5 actually. And so we get a lot of borrowed help. You see a lot of black names there, and that's from the regional swamp coordinators and other support staff from the regional board. Some of them are probably in the room today. And they voluntarily help us make sure that data gets in there. And so we are eternally grateful for that, and making sure that we are communicating those advisory and health risks to the public in pretty close to real time. So now I'm going to dive into the features of our HAB map. So the map provides information as to the type and severity of a health advisory by the coloring and the shape of each point on the map, focusing primarily on that freshwater and estuarine HABs. The colors also denote the type of advisory, which is going to complement the same advisory signage and coloring that you'd see on the ground at these water bodies. So the circles identify those planktonic blooms, and then the triangles signify the benthic blooms. We also, in the last 2 years, have started sharing information on red tides as we've been receiving it from the public. And so those are identified with the blue square icon. We also do keep some historical information on the map. So you might notice those lighter yellow and the gray circles. So those are reports that haven't been updated and are more antiquated, 30 plus days old. We do keep these on the map, and it's important for us to do that because we don't often have regular monitoring programs for a lot of these water bodies. So that is the most up-to-date information we do have for the public, and we feel it's important for them to have some information rather than no information. And then the public can also toggle between years. So the current year is always the default, but they can always look at historical years to see if HABs are a consistent issue for the water body of concern. And then what makes this Tableau map unique is that it's actually automatically updated with database information twice a day. So that's, once again, to ensure that pipeline of data sharing with the public is in near real time. Okay, so now if you kind of deep dive into each water body, if you click onto an icon, which is usually signifying an advisory for a water body, additional site-specific information pops up for each report. So this will include location, often with the latitude and the longitude, any water body manager or land manager information, who provided that information, whether it was from a routine monitoring program, from the water body manager, or internally from the water boards, when that information was last updated for the report. So as I said, staff are in there all the time, updating information with new data as they receive it, or anecdotal information, and then the current advisory and associated advisory recommendations. And as well, any report details. So these are really important, especially for the public, because it can include if an advisory is based on just visual observations of a bloom, and that is usually verified with photos or staff going out there to verify. If the information is based on water sample results, so that's where you're going to get more information to determine if it's at danger or warning advisory. If the data comes from a routine monitoring program, so the public can assume that there'll be more data coming in as the season goes. If there's an associated reported HAB-related illness investigation ongoing for that water body, et cetera. So these details are updated by staff all the time, especially during the HAB season. You can also, so you can use the actual map in the water bodies and click on that. But also on this map, if you look on the right-hand side, there's actually a table that's displayed. So the public can access information based on the county or water body, and this table can also be downloaded. So it's just another way for the public to query based on the information that they're of interest. And I just accidentally kept going. Sorry about that. So some other cool map features that facilitate this easy sharing. If you look at the bottom right-hand corner of the slide, you can actually grab a link from the map to share information about individual sites. So like the water board staff or the public can go in and be like, this is the water body of interest, and these are the advisory details of interest for that water body. They can get a handy link and stick it in an email, and then that'll direct that individual they're trying to share it with just the specific information they want to know about that water body. And we're constantly working on providing all this metadata and then also any corresponding monitoring data, also accessible in our open data portal platform as another pathway to have this information available. So as you can see, with the different presentations with Michelle and me, we've developed different dashboards based on different needs. So the swamp data dashboard is designed for that long-term data sets, and the HAB map was really designed for that immediate data sharing. And so rather than sharing the raw data like the swamp data dashboard, it communicates recommendations based on that data. But they're both developed to communicate data in a more consumable way. And as Michelle said, we're constantly working on updating based on input. And as we get advances in how we share data on both dashboards. And so we like to consider them both a work in progress. So with that, we welcome you to reach out anytime with any comments or suggestions. There's some emails right there. And then you can also access these different dashboards with the links here or the QR codes. And so please check them out if you haven't already. And with that, we'll take any questions.
All right, we have time for maybe one quick question.
So you mentioned that the HAB map gets updated twice a day, right? So I guess my question would be, from the time that you actually receive data, how long does it take to get posted on the map for public to see?
That's a great question. So we either input the data ourselves as the water board staff, or we get the data from the public, and so then it's QA'd by staff. And we have business rules that we try to do it within 2 days. So, and then because it's updated on our Tableau map, that's usually, as I said, 48 hours, unless it's a weekend.
That's reporting data, not like the water quality.
Right. So Anna suggested clarifying that the data that Carly's talking about is the reporting data. So reports that we receive reporting incidents of algal blooms. So it's not the actual like monitoring data.
Correct. And the associated advisory.
From an anonymous attendee, what management activities besides notification are undertaken when HABs are identified?
What other actions? Well, anytime we receive a report, that triggers our incident response procedures, which includes going out to either verify that there's a bloom, communicating with the county and water body manager for any response. And then if we can either get visual observations in our water quality data, then we recommend putting actual postings on the ground, and our program actually provides signage for those purposes.
And let's thank our speakers, and we'll transition to our next. Okay. I'm happy to introduce Stephen Huie. Let me get, he has his title here. He's going to talk to us about building a freshwater harmful algal bloom assessment toolbox using a multifaceted approach to evaluate the causes of blooms in Lake Eastman and Lake Hensley.
Yes, thank you, Jayme. So like Jayme said, hi everyone, my name is Stephen Huie. I'm from the Central Valley Regional Water Quality Control Board, and that's a long title, so I'm not going to say it again. I'd like to thank everyone, my co-authors, including Jayme. But yeah, let's get started. Good clicker. I guess we won't get started.
Now we started.
Okay. Okay, so starting off very basic. So why assess harmful algal blooms? So harmful algal blooms, or HABs, can impair beneficial uses such as drinking water, wildlife, recreation, and can produce toxins that pose health risks to humans and animals. Reports of blooms have been increasing in recent years, with more places reporting higher levels of biomass and toxin. And so we're concerned about these increases in HABs, and there's many possible drivers such as eutrophication, climate change, and hydromodification that could be responsible for this increase. And so to further investigate HABs, we chose to focus on two lakes, Lake Hensley and Lake Eastman, which are experiencing chronic HAB issues. So they're both created and maintained by the U.S. Army Corps of Engineers, and they're very similar in size, climates, and geographical location, being only about 9 miles apart from each other. And they're located in the Sierra foothills, about 35 miles from Fresno, California. So both experience consistent impairment due to HABs and have frequent recreational warning signs for toxins. And so we can see we have a map in the top right where the lakes are located. We have a lovely picture of Lake Hensley, and then below we have a recreational toxin warning that mentions both lakes. And so moving on to some of the data that we saw at the lake. So despite the similarities we just described, we can see that there's a clear difference between toxins between the two lakes. So here we have a bubble plot showing the toxin detections and health concerns based on the California cyanobacterial and harmful algal bloom, or CCHAB thresholds. So on the y-axis, we have our two lakes, Lake Eastman on top and Lake Hensley on the bottom. And then our x-axis is just months and years for the duration of the study. And so each circle represents the max toxin found during the month at each lake. The color represents the CCHAB toxin level, and then the size represents the toxin concentration. And so we can clearly see that between the two lakes, they both have detections, toxin detections, but Lake Hensley clearly has more frequent and larger toxin. Hello? Okay. So this begs the question, why do the frequency and severity of HAB events at Lake Hensley differ despite their similarities in environmental and recreational use? And so providing some more context on how we conducted this study. So samples were collected monthly from May 2021 to December 2022, with bi-monthly sampling occurring between May and October for both lakes. Both lakes had 3 sampling sites, one on the western shore, the eastern shore, and tributary inputs from the Fresno River into Lake Hensley and the Chowchilla River into Lake Eastman. And so from each of the sampling locations, we collected chlorophyll A, nutrients, cyanotoxins, and field measurements, and also looked at dominant species. And in addition to in situ data, we also downloaded hydrological data, land use data, and remote sensing data to better characterize the two lakes. And so we first started looking at chlorophyll concentrations. So here we have a time series of chlorophyll just on Lake Eastman. The y-axis is chlorophyll in micrograms, and the x-axis time. So we have 2 different color lines. Those are the 2 different shoreline stations. And then the dashed line at lower one is the average chlorophyll for the entire study, which is around 40 micrograms per liter. And then the dotted line above it is 1 standard deviation above the mean. And so we can see at Lake Eastman, there's high chlorophyll locations, but infrequent blooms and higher variability, with chlorophyll levels being either well above or well below the average concentration. And then in terms of seasonality, Lake Eastman has increased biomass in July through October in both years. And in between the summertime blooms, there are lower chlorophyll averages during the winter and spring. So next we have Lake Hensley chlorophyll in the similar figure. We can see that Lake Hensley has a higher baseline chlorophyll concentration with more frequent blooms than Lake Eastman. The seasonality, however, is similar to Lake Eastman with blooms during the summer, but unlike Lake Eastman, Lake Hensley has above average chlorophyll during the late fall and winter until February 2022. And then after February, Lake Hensley falls to similar chlorophyll levels as springtime levels in Lake Eastman. And so we can put those two lakes together as a side-by-side, and we can see overall both lakes have similar average biomass, but very different bloom dynamics. So you can see the dashed line for both lines are pretty similar to each other, but we do see that the standard deviation at Lake Eastman, which is the dotted line, is almost double the standard deviation at Lake Hensley. And so moving on to the more different bloom dynamics, we can see the more extreme chlorophyll concentrations, especially in the summer of 22 in Lake Eastman, but this contrasts the more or the less extreme but more consistent high biomass seen in Lake Hensley. In Lake Hensley, we can see most of the observations are above the chlorophyll mean, while Lake Eastman is usually below, except for its extreme values during the summer. And then, as we previously described, both lakes have similar summertime seasonality, but Lake Hensley is unique with its late fall and winter bloom, with both lakes returning to similar chlorophyll during the springtime. And so moving on, we also looked at microsystems. So in a similar time series, we have just Lake Eastman right now, and we also have the CCHAB level thresholds as the dashed lines. So above yellow is caution, above orange is warning, and above red is danger. Overall, we had minimal toxin detections in Lake Eastman with 57 microcystin observations. Only a third of them had detectable microcystin, and of that third, only 30% had a CCHAB level of caution or greater. We can see in the figure that most of this happened during the summer of 22. And while there were other below caution microcystins throughout the year, they primarily occurred during the summer of 21. And then switching over to Lake Hensley. So we can see that there's much frequent and higher toxin levels at Lake Hensley. During the study, over 50% of observations had microcystin detections. And of those observations, 60% of them had a caution level or greater. In Lake Hensley, you can see a majority of the caution or greater concentrations occurred in the fall of 21, at the beginning of 22, and at the end of summer 22. And similar to Lake Eastman, there were below caution detections throughout the year. And so just like chlorophyll, we're looking at them side by side right here. And so we can see the more frequent and intense microcystin detections at Lake Hensley. Then despite both lakes having their microcystin peaks during the summer of 22, Lake Hensley had much greater microcystin concentrations, which is the opposite of Lake Eastman, which had greater chlorophyll concentrations during the same time. And then we also found additional toxin detections for anatoxin and cylindrospermopsin, but microcystin was the most dominant, so we decided to focus on that. And so expanding on the toxins and chlorophyll that we just looked at, we looked at them together. So here we have a scatter plot with chlorophyll on the x-axis and microcystin on the y-axis. Both axes are on a log 10 scale, and the colors and shapes are separated into years. So we have the red circles from 21 and the green circles from 22. And then the ellipses are just there to help visualize the years. And so visually, we can already see that there's a more consistent relationship between microcystin and chlorophyll in Lake Hensley for both years than in Lake Eastman. In Lake Hensley, microcystin and chlorophyll seem to have the same slope for both years, but we do tend to see lower microcystin levels in 21 and higher levels in 22. In Lake Hensley, there are fewer observations, but there's still a similar relationship between chlorophyll and microcystin in 22. However, we see a very different relationship in 21 with just the small cluster in red right there. And so these visual relationships line with our numerical correlations, as chlorophyll and microcystin are correlated for the overall study, and in 21 and 22 for Lake Hensley, but just 22 for Lake Eastman. And it's also important to note that the range of chlorophyll with detectable microcystin is similar to the range of chlorophyll without detectable microcystin. So this suggests that chlorophyll is not a good indicator of microcystin in these particular lakes, but we do typically see high microcystin detections occur simultaneously with higher chlorophyll. And then even though we do see And then even though we do typically see higher biomass in Lake Eastman, we see a similar, if not lower, toxin concentration compared to Lake Hensley. And so this suggests that there are likely other factors influencing toxin. So moving on, we have other potential drivers. So we found that there are mostly similar between the lakes. So we looked at the land usage, and so both lakes are surrounded by undeveloped land with minimal upstream development agricultural land uses. And then on the right, we have nutrient time series. So we have total phosphorus and total nitrogen, and we can see that they have very similar seasonality with higher levels during the summer and lower levels during the winter and spring. And we also see the dashed line again, which is the average chlorophyll for the year, which are pretty similar in both lakes. And then we also looked at the tributary inputs of nutrients. And so we found that on average, the Chowchilla River and Lake Eastman has a greater input than the Fresno River into Lake Hensley. And so to better look at the tributary nutrients into the lakes, we also looked at the hydrology data. And so here's inflow in red. And then so overall, there's more consistent and higher inflow in Lake Hensley and lower and intermittent flow in Lake Eastman. Lake Hensley had relatively higher inflow throughout the year with overall average 3 times greater than Lake Eastman. And then there's minimal inflow during the summer and fall with greater inflow during the winter and spring, which makes sense. And then even though that both lakes are close geographically, it's unsurprising that they had a similar, never mind. So we see that they both, they have a large peak in December, and because they're both close geographically, it's unsurprising that they occur at the same time. However, what is surprising is that despite both lakes having that large inflow event, Lake Hensley has more input following during the winter and spring that Lake Eastman does not. And so moving on from lake inflow, we also have outflow. So both lakes routinely have outflow periods during the beginning of July and have similar outflow rates. Lake Hensley does have longer periods of outflow during these times. Lake Hensley does have a larger inflow, 3 times greater than Lake Eastman, just like inflow. And another thing to note is that Lake Hensley has additional outflow during the winter and spring that Lake Eastman does not, and this is likely due to the inflow that we saw previously. And so combining all of the things we looked at before, we have inflow, outflow, and chlorophyll in green. And so overall, we see that Lake Hensley has a much closer relationship with hydrological data and chlorophyll than Lake Eastman. Hensley corals is correlated with outflow and inflow, while Lake Eastman is only correlated with outflow. We can see a slight inverse relationship between chlorophyll and inflow more so in Hensley and is less consistent in Eastman. Inflow is low during the summer and fall and higher during the winter and spring, which is the opposite of chlorophyll. And then in terms of outflow, we see large blooms of chlorophyll during and shortly after the July outflow periods right there that you can see in the box. And then we also see small chlorophyll blooms in both lakes after the large inflow period in December right there. And so both the inflow rate and subsequent bloom during these times were higher in Lake Hensley than in Eastman, and we also see higher biomass during these times in Lake Hensley as well. And so overall, we see that there's higher and more consistent rates of biomass and inflow in Hensley, while there's more intermittent and lower biomass concentrations in Lake Eastman. So lastly, we also have microcystin adding on to that as well. So there's minimal correlations between hydrological data and toxin in Lake Eastman, with toxins not correlating with any hydrology in Lake Eastman, but they are correlated with inflow and outflow in Lake Hensley. The lack of correlation between toxins and hydrology in Lake Eastman could be due to minimal microcystin detections. And just like the scatter plot we saw from before, we saw that microcystin detections usually occur with higher levels of biomass, and the majority of high detectable microcystins do not, but the majority of high detectable microcystin observations do not directly align with outflow or inflow, but we do see them to be delayed afterwards, just in the same spots that we saw as chlorophyll. And then summarizing all of this, we have a diagram that summarizes the toxin, hydrology, and chlorophyll that we just talked about. So we have more input into Lake East. The input into Lake Eastman has higher nutrient concentrations with a lower inflow rate, causing less dilution of nutrients in the lake. There's minimal outflow except for in July, occurring once a year, flushing the lake. And these two factors together create a longer residence time, which allows nutrients to accumulate and form extreme blooms. And then because of the intermittent flow, we see lower chlorophyll concentrations whilst on summer. And so overall, because of low biomass and less nutrient dilution, Lake Eastman might favor less toxic dominant species. So there's less opportunity for high toxins and frequent toxin detections. And then we look at the same diagram in Lake Hensley. And so the input into Lake Hensley is lower nutrients with a much higher inflow rate, causing the dilution of nutrients. In addition to consistent and higher outflow rates, Lake Hensley has a shorter residence time. This causes more flushing and limiting the magnitude of blooms such that chlorophyll isn't as high as Lake Eastman. And then because there's a more balanced inflow into Lake Hensley, we get a higher, more consistent baseline chlorophyll level and more potential blooms during the winter. So due to higher chlorophyll baseline levels and occasional spikes in TP and TN, Lake Hensley might favor more toxic dominant species, allowing for more frequent and higher toxin concentrations. And so this overall answers our question, or starts to answer our question, on why the lakes differ in biomass and toxins. And we found that the individual lake flow and outflow together alter residence times and nutrient dilution, and therefore can cause differences in biomass and toxins. And that about wraps it up, and I'm happy to take any questions.
Let's take any questions.
Thank you. Very good presentation. I have a question about fish stocking. Are they both stocked the same? Sometimes there's top-down impacts from fish, especially on chlorophyll and nutrients, and wondering if that was considered at all or different between the two water bodies.
Yes, thank you for that. I know that they are both stocked with fish because they're pretty popular recreational fishing spots. In terms of how they are stocked, I'm not sure about any differences between them, but that, of course, might be a possibility of why there's differences in blooms and toxins.
I had a question about the stratification cycle of the lake. Did you look at all the timing of that versus the blooms and when the nutrients were spiking?
Yes, thank you. That is a good question. So we do know that Lake Eastman is deeper. It's about 7 meters, while Lake Hensley is about 40 meters. And that's something that we want to look at, but haven't had the chance to look at. So not yet, but we'd like to.
Two short questions online. The first one is, do both lakes have similar depths?
No.
No, yeah. I'm just reading it. Yeah. Are either or both man-made or natural lakes?
They are both man-made.
Any other questions for our speaker? Awesome. All right. Thanks, Stephen, for a great talk. All right. Thank you. My name is Jayme Smith. Again, I am a SCCWRP scientist and I work on harmful algal blooms. And so I'd like to thank my long list of co-authors on this study, including Stephen, who did some great data analysis work on this project. And so I'm going to talk to you today about some work we did to do some historical kind of analysis on water quality in Clear Lake, and then some more recent field studies to look at harmful algal blooms in this system. So Stephen did a nice job of setting up harmful algal blooms. So I'll start with just how detrimental they are in the Clear Lake system. They basically impact all of the key beneficial uses within Clear Lake. Recreation, Clear Lake is a big bass fishing center, as well as a lot of other recreational sports. Drinking water, there's a lot of drinking water sources within Clear Lake, as well as really important tribal and cultural uses. There's multiple indigenous people groups around that lake. Angela did a good job of mentioning them at the beginning of this talk, as well as fishable and aquatic life habitat in this system. And so what we kind of wanted to do with this study is kind of look at some of the historical data within this system. There's a lot of work that's been done because Clear Lake has had a lot of kind of issues related to mercury and other kind of impairments. It's on the 303D list for a number of issues. And so there's a lot of just historical, going back to the 1950s, water quality data. And then we wanted to look at that data in relation to some of our more recent information on cyanobacterial harmful algal blooms and see if we could figure out any kind of historical changes in the lake, and then pair that with some more recent environmental observations within the lake. So I'll highlight a little bit of the historical synthesis as well as some of the ongoing cyanohab work that we're doing in this system. So for the historical data synthesis, I think Michelle did a great job of kind of teeing up the importance of this data. We looked at a number of historical databases, CDIN, NOAA, USGS, Vector Control, and Division of Water Quality, dating back to the 1950s, as well as some of the tribal government monitoring data from this system. We ended up with a database of over 200,000 data points with 60 plus stations, looking at a combination of water quality and hydrology and climatology. And the cyanohab data is probably the least plentiful of all of the water quality data. But we were able to glean some kind of cool insights into how the lake has changed over time. So starting with just kind of the HAB story here is that there's a history of extreme cyanotoxin concentrations. I think I kind of already established that. But cyanobacteria and cyanotoxins were first documented in the lake in about 2011. They were there previously, but this is kind of the first systematic study of them right here in 2011. And then the tribal governments around the lake established a routine monitoring program in 2014. And in subsequent years, they basically kind of observed cyanotoxins well above the human health threshold. So we have the CCHAB trigger levels that Stephen showed in the previous talk, where this is the caution. Anything above this line gets a caution posting. Anything above this dashed line here is a warning, and anything above this dotted line is a danger. This is on a log scale, and so that is 10,000 micrograms per liter. So there's some orders of magnitude greater than the danger level observations in this system. There's also observations of another cyanotoxin called anatoxin A, much less frequent. This is a microcystin dominated system. And so kind of looking at, that was a kind of an annual view of what are the maximum kind of concentrations that we're seeing. When you look at that kind of in a seasonal aspect, you see that there is kind of a strong seasonality, much like Stephen showed in Lake Hensley and Lake Eastman. Lake Clear Lake has kind of a seasonal pattern to when you see your maximal microcystin concentrations, with toxin concentrations increasing from about the late spring in through the early fall, peaking generally in either August or September. And so one of the first things we wanted to look at is this a climate change issue? And so with almost 70 years of data, we wanted to just see, okay, is it just temperature? Because cyanobacteria love warm water. And so when you looked at temperature, kind of over a year-over-year trend, we saw no trend, which was actually kind of surprising. We were expecting to kind of just see, oh, it's getting warmer. So we kind of dug deeper and we looked at, are the temperatures within a given month getting warmer? So this is kind of a complicated plot here. But what you're seeing is that seasonal cycle and temperature that you would expect in a lake. And then these blue lines are our trend lines for that given month. And so I want to draw your attention to kind of the transition from spring to early summer. Is in these months, we're seeing kind of a rapid increase in temperature over time between I think we started this in 1960 into 2020, especially in kind of May, where you're seeing this much more rapid increase of warming temperatures in the springtime. And so one thing that we think is going on here is there's a shift in the temperature and the transition into summertime that's allowing early onset blooms of cyanobacteria. They're able to kind of take hold, and it kind of pushes out your other phytoplankton that like cooler water, like diatoms, kind of out of the system and favoring cyanobacteria earlier. We also looked at some of the phosphorus levels. As I mentioned, Clear Lake has a TMDL in place for phosphorus. And so they have a chlorophyll target of 73 micrograms per liter, and they're looking to reduce their phosphorus loads. The TMDL went in 2007. So we leveraged our data set to kind of look at the 10 years before the TMDL and the 10 years after the TMDL. And so I want to kind of just show you that, unfortunately, the phosphorus levels went up in the 10 years after the implementation of the phosphorus TMDL. And so you can kind of look at, this is a probability density plot. And so the red color is the distribution of observations after, and the blue is before the implementation of the TMDL. So you can see the blue, the probability of getting some lower measurements is a lot higher before the TMDL. And then you still get lower measurements, but you kind of get an increase in probability of higher measurements. It's not a huge increase, but basically you're not seeing the decrease in phosphorus that was hoped with the implementation of the TMDL. And so there's a lot of reasons for that, one of them being that there might be kind of an internal nutrient loading issue in this lake. And so we did a lot of other analyses. So I'm going to do a shameless plug for our paper that just came out on Friday on this topic. It is on an open source journal. I'm happy to share it with anyone who wants to kind of look at the rest of the analyses. But I want to kind of transition. We identified some key data gaps that we think would be important for kind of better understanding the cyanobacterial ecology in the lake. And I'm going to focus on two of those today, which is looking at community composition dynamics across finer scales to kind of better understand the initiation of bloom events in this system. And so there was 2 field surveys that were conducted. We did a every other day sampling in the August 2020, which was kind of fun during COVID. And we did monthly sampling from June to October in 2021 to try to capture that kind of entire bloom period. We did 10 stations a day over 8 sampling days. And we characterized kind of algal biomass via chlorophyll A, cyanotoxins, nutrients, community composition, and other water quality characteristics. So we're still working on this. I'm going to just give you kind of a preview of what we found. So this is chlorophyll here. I'm going to show you on the top. This is going to be the every other day survey through the month of August. And this is kind of monthly observations from June to October. And so this line here is the TMDL target for chlorophyll. In 2020, we see several exceedances of that chlorophyll line. In 2021, it was a very exceptional bloom year. So we see many, many exceedances. These are on different scales. So this is, again, several orders of magnitude above the TMDL target for chlorophyll. And that kind of mirrors what we see with the cyanotoxins. So this is total microcystins. Again, please note, these are on different scales. This is 6 and this is 200. And so basically we see the 6 level, this is caution level. So there's basically roughly about caution or below concentrations for the entire month of August in Clear Lake in 2020. Whereas when you look over the seasonal cycle in 2021, we're seeing levels up to 200, which is about 10 times higher than the danger level for microcystin. And so what we're working on right now, and this is a lot of colors, but we're looking on using molecular approaches. So plug for Susie's eDNA session later. But we're using molecular approaches to better understand community composition and transition over time. And so here I'm just pulled out what we did in 2021, looking at composition over a couple of different months. And what we can see in some of these stations is some interesting shifts in some toxin-producing taxa. So this is microcystis. And you can see how that community at this station kind of shifts greatly into September, which is when we had those really, really high microcystin levels in this location. And then it kind of drops back down as the community shifts. So we're going to work on looking at some of the community composition at additional stations. And this is Isha Carla is working on this. She's taking the lead on this part of the work. She's also looking at the algal community and looking to see if we can tease apart any relationships with the other members of the phytoplankton community, like green algae and zooplankton and things like that. So stay tuned. We have some more work kind of coming using molecular approaches on community composition. And so to wrap up, Clear Lake, unfortunately, has chronic microcystin levels over many years, well exceeding the danger level, probably capturing some sort of world record at points for microcystin levels at 10,000 micrograms per liter. Not really the record that you want, but historical analysis points to some key changes in kind of the seasonality of the lake. The TMDL, as far as looking at phosphorus in the water column, the TMDL has not really had the effect that was hoped so far. And we do see a loose but kind of common relationship with the biomass. We tend to see higher biomass with higher microcystins, but as Stephen said, it's not a perfect relationship in most lakes, and that holds here in Clear Lake as well. And we're working on more work to better understand the community composition within Clear Lake. So with that, again, I'd love to thank my co-authors and all of the people that put a lot of effort into this study. And I don't know if I have time for questions.
Not so much time.
Okay, perfect. All right. Love to take any questions. Yes.
I know. Thank you so much for this. Thanks for the work. I help manage Clear Lake, so yay, number one, I know. Just kidding. So you guys are studying a lot and diving into the cyanobacteria community composition. The differences of what triggers certain communities to be dominant, what doesn't, how that changes, which is really hard because we have a patchwork of data. And as a manager, how does that help us manage a lake and put in place mitigation techniques, like the information that is being produced from a deep dive study on the different types of cyanobacteria and genera? How does that help me as a manager? What information does it give me to then put in place on the ground that can mitigate and reduce the severity or the frequency of these blooms? Thank you.
Yeah, happy to answer that. I think there's a couple of things that we can learn by understanding the community composition. Cyanobacteria are really kind of diverse, interesting critters. So we have a mix of nitrogen fixing and non-nitrogen fixing cyanobacteria. And so one of the things, there's a couple that plot is really rich, but you have shifts at some places from nitrogen fixing to non-nitrogen fixing cyanobacteria. And so understanding kind of, okay, these are critters that either can use their own nitrogen, or they need, microcystis is a non-nitrogen fixer. So if there's lots of nitrogen present, that gives them more fuel to make cyanotoxins, right? And so there's a phosphorus TMDL, but there's not a nitrogen TMDL, for example. So if you understand kind of that, there's other critters that can transport up and down the water column. One of them is called Galeotrichia, and there's evidence that they can go down to the sediment and bring up and internal phosphorus loads into the photic zone. So just understanding the nuances of the critters kind of gives you some more detailed information about what you might want to do and what kind of actions you could take to address the bloom that's happening. Any questions?
Yeah, thank you. That was really interesting. The one question I had was regarding the eDNA plot. It looked like for microcystis, you saw the blooms pop up in some arms, but not other portions of the lake. What do you attribute that difference between different portions of the lake where you saw the huge increase in microcystis and not others?
Yeah, that's a really great question. Thank you for asking that. I think there's a difference in kind of it's a very large lake. It takes like over an hour to drive, and so there's lobes of the lake. They kind of function almost like independent lakes. So the lower, and Angela, I'm gonna probably butcher it. You're the true expert on the system, but the lower two arms are a lot more shallow. And so we think that there's different kind of mixing dynamics than the upper arm that might kind of contribute to kind of distinctive communities across kind of the different lobes of the lake. I thought I saw, yeah. Here.
I had a question that was more kind of a reach of a question. So sorry, Jayme. Based on this, really nice data set you have, 70 years, does this go towards answering kind of getting at a question of what starts a harmful algal bloom? Or at least in this system, can you kind of say what might trigger a harmful algal bloom? And then for managers, how can you curtail or stop that?
Thanks for an awesome hard question. That's a really great question. I think, that's why we started with temperature. That's not really a knob in a lake that a manager can turn. So we were like, kind of like, well, this is something that, okay, springtime kind of starts earlier. I don't know what you can do to manage that. And that's kind of like, sorry, Angela. Some of the things that we looked at as well were lake level management. So Stephen talked a lot about that at Lake Hensley and Lake Eastman. There is some kind of relationships between lake level and intensity of the blooms. I didn't have time to kind of show that. But that's maybe a more likely knob that could be turned. And then obviously there's a pretty strong relationship with nutrients. And so maybe we need to kind of, and the Central Valley Water Board is kind of reevaluating some of the TMDL, who's in compliance, do we need to consider other nutrients? So there's a couple knobs. There's also things like climate that unfortunately we don't have that knob to turn. Other questions? All right. Well, thank you so much. And thanks to all of our speakers in this session, Michelle and Stephen and Carly on the phone. I think we're going into lunch.